In this video, we're going to talk about the pH scale. And in order to understand pH, we need to talk about the ionization of water, or Kw. As we've seen, water can act as either an acid or a base, and that will depend on the environment it's in. If it's in a basic environment, it will act as an acid. If it's in an acidic environment, it will act as a base. This is not unique to water. A lot of different things, especially multiprotic acids or polyprotic acids, can act as acids or bases. This is known as being amphoteric. The water is amphoteric, which means that when it reacts with itself, one of these water molecules can act, and one of them will act as a base. So when one of them acts as the base, it's going to accept a proton and become hydronium ion. And then the other one, since it donated the proton, it will become one of these waters is going to act as my acid, and one of them is going to act as a base. When the base accepts a proton to become hydronium ion, the conjugate is hydronium ion. When the acid donates a proton, it becomes hydroxide. Hydroxide is the conjugate base. In solution, if you ever have hydronium, it will always be the conjugate acid. If you have hydroxide as a product in your reaction, it will always be the conjugate base when we're talking about the dissociation of acids and bases. So we can write an equilibrium expression for this process. And instead of using KEQ or KC, we do KW for water. And this is going to be equal to the concentration of hydronium ion times the concentration of hydroxide. And the equilibrium constant for this process is 1.0 times 10 to the negative 14. Remember, we do not exist, or we do not put liquids in our equilibrium expression, so that's why we only have the products present and we don't have the reactants. If you have a neutral solution, means we have equal parts of our acid base. If we look at how water dissociates, hydronium ion is the acid part and hydroxide is the base part. What that means is the concentration of hydronium ion for a neutral solution must be equal to concentration of hydroxide. And since we know that Kw is equal to the concentration of hydronium ion times the concentration of hydroxide, and we know that that has to be equal to 1 times 10 to the negative 14, that means when you have a neutral solution, the concentrations have to be equal. They both need to be equal to 1.0 times 10 to the negative 7. Because 1.0 times 10 to the negative 7 multiplied by 1.0 times 10 to the negative 7 is going to equal 1.0 times 10 to the negative 14. If we have an acidic solution, that means that we will have more acid than base. So the concentration of our hydronium ion is going to be greater than the concentration of our hydroxide. Also means that the concentration of hydronium ion must be greater than 1.0 times 10 to the negative 7 molar, because that's when we would have a neutral solution. So it needs to be greater than that. In a basic solution, we have more base than acid. In this case, the concentration of my hydroxide needs to be greater than the concentration of my hydronium ion. So the concentration of my base is greater than the concentration of hydronium ion. We can also say that the concentration of hydroxide must be greater than 1.0 times 10 to the negative. We can use the equilibrium expression for the dissociation of water, or we can use Kw to solve for the concentration of hydroxide or hydronium in solution. Let's look at an example of how to do that. We have calculate the concentration of hydroxide in a solution if the concentration of hydronium ion is 2.31 times 10 to the negative 7. So Kw is equal to the concentration of hydronium ion times the concentration of hydroxide. And I also know that Kw is equal to 1 times 10 to the negative 14. So if I want to solve for the concentration, then I can do that algebraically, and I will get Kw over concentration of hydronium ion. Now we have a plug and chug situation. We have 1.0 times 10 to the negative 14 divided by 2.31 times 10 to the negative 6. And what does that equal? Go ahead and get your calculators out and plug that. So I get 4.37 times 10 to the negative 9. And remember, we're solving for a concentration, so my units are going to be concentration. If we want to calculate the concentration of hydronium ion in solution, then we can solve for that algebraically, just like we did with hydroxide. Now my equation is going to be Kw over the concentration of hydroxide. So we have a plug and chug situation. I have 1.0 times 10 to the negative 14 divided by 4.53 times 10 to the negative 3. When I plug that into my calculator, I get 2.23 times 10 to the negative. Finally, we have calculate the concentration of hydronium ion in a solution if the concentration of hydroxide is 1.0 times 10 to the negative 7. So I recognize that this is the concentration for a neutral solution. So the concentration of hydronium ion needs to be equal to that. So let's solve for this mathematically. The concentration of hydronium ion is equal to Kw over the concentration of hydroxide. I can plug my values in, 1 times 10 to the negative 14 for Kw, and 1.00 times 10 to the negative 7 for hydroxide, and that gives me 1.0 times 10 to the negative 7 for the concentration of hydronium ion. Now we can determine if these solutions are acidic or basic, and all we need to do that is compare the concentration of hydronium ion to hydroxide. So in our first example, the concentration of hydronium ion is 2.31 times 10 to the negative 6. And the concentration of hydroxide is 4.37 times 10 to the negative 9. When you are comparing these numbers, remember, we don't want to look at the number portion of it. We want to look at the magnitude of it. And the more negative your exponent is, the smaller the number will be. So in this first example, the concentration of hydronium ion is greater than the concentration of hydroxide. So that means we are dealing with an acidic solution. In our next example, my hydroxide is 10 to the negative 3, it is 10 to the negative 12. So in this case, the concentration of hydronium ion is less than the concentration of hydroxide. So that means we have a basic solution. In my final example, I notice that they are the same. So the concentration of hydronium ion is equal to the concentration of hydroxide. So this is going to be a neutral solution. Now, when we're talking about whether a solution is acidic or basic, it's not the most efficient use of your time to talk about it in terms of concentration, right? Like, oh, the P or the concentration of hydronium ion is 2.23 times 10 to the negative 12, so it must be in an acidic solution. Since these are all going to an exponent written in scientific notation, we can use a log to make it a number that we can deal with that is going to be easier to talk about and easier for people to understand. That's where we cut pH scale. The pH scale is directly related to the concentration of hydronium ion. So you can think of it as parts of hydrogen in your solution. And we use this to measure how acidic or basic a solution is. Now, this is very important. In order to solve for the pH, you have to have the concentration of hydronium ion. Sometimes this will be written as pH is equal to the negative log of the concentration of H. Remember, those really mean the same thing. When we have a neutral solution, we already saw that the concentration of hydroxide and hydronium ion have to be equal to each other, and that is when the concentration of hydronium ion is equal to 1.0 times 10 to the negative 7. So we can plug that into our equation to solve for the pH. And we can take the negative log of 1.0 times 10 to the negative 7. And that is going to give us a pH that is equal to 7. Well, for a neutral solution, your pH is going to be equal to, if you have an acidic solution, then the pH is going to be less than 7. If you have a basic solution, the pH is going to be greater than 7. So let's look at some examples. Calculate the pH for the following solutions. We just did this one. pH is equal to the negative log of 1.0 times 10 to the negative 7, and that is going to be equal to. Now, keep in mind that logs are base 10. When you're doing the log, you need to be looking at the exponent. Or just take the straight up log of 1.0 times 10 to the negative 7, it would give me negative 7. So that's why we have this negative sign out in front. So we multiply these two negatives by each other and we get a positive number. If you have the number portion is equal to 1, then the log of it is going to be equal to the exponent. If your number portion is not equal to 1, then the exponent, the pH is not going to be equal to the exponent. Let's look at an example of that. In B, I have the pH is going to be equal to the negative log of 3.2 times 10 to the negative. That is going to give me a pH value equal to 3. In C, you need to be very careful because notice we don't have the concentration of hydronium ion, the concentration of hydroxide. That means I need to calculate the concentration of hydronium ion before I can plug it into my pH equation. So just like we did previously, I can use Kw is equal to hydronium ion times the concentration of hydroxide, and that is equal to 1.0 times 10 to the negative 14. For the concentration of hydronium ion, it is going to be equal to Kw divided by the concentration of hydroxide. I can plug my values in. 1 times 10 to the negative 14 divided by 1 times 10 to the negative 9. And this is going to give me a hydronium concentration of 1.0 times 10 to the negative 5. Now I can plug that into my pH equation. I can take the negative log of that. My pH is going to be equal to, now in number 2, we are going to be reversing the log. pH is equal to the negative log of the concentration of hydronium ion. To reverse the log, you need to take it into the both. Right? And so if I want to get the negative sign, I can move it over here. And then that is going to be how we can reverse the log. It gets rid of the log. So now hydronium ion, the concentration of hydronium ion is going to be equal to 10 to the negative pH. So if you know your pH value, you can solve for the concentration of hydronium ion. I'm going to plug that in right here. I have 10 to the negative 8.5. This is very important. We do not express exponents with decimal points. So writing this as 1 times 10 to the negative 8.5 is not correct. You need to put that into your calculator. And when we do that, we get 3.16 times 10 to the negative 9. That is the concentration of my hydronium ion. To get the concentration of hydroxide, I'm going to plug this into my Kw equation. Kw is going to be over the concentration of hydronium ion. We have 1.0 times 10 to the negative 14 over 3.16 times 10 to the negative 9. That means the concentration of my hydronium ion is going to be equal to 3.16 times 10 to the negative 6 molar.